pi to pi may not be square integrable over minus pi to pi. Okay. Right. So in this section, we will consider a square integrable function. Okay. Now, since it is absolutely continuous, so it can generate a trigonometric Fourier series. So let A0 plus summation n from 1 to infinity an cosine nx plus bn sin nx. Okay. B the trigonometric Fourier series. Okay, generated by f. And we know how to calculate the coefficient, right? Right, so A0 is just this integral, and the A sub n is 1 over pi. And cosine x dx, right? And it's just integral. Okay, and Bn. Right, now, no matter whether the series A0 plus whether the series converge to fx or not in any sense. Okay. For example, in section 11.1, we prove for a representative theorem, which says that if f of x is a periodic function with period to pi, and it is piecewise continuous, the final crescendo interval from minus pi to pi, and has a left hand and right hand derivative at every point. In that case, then the trigonometric Fourier series, okay, will converge to f of x at every point x where the function f is continuous. Okay, so we have that situation. Okay, and if at the point x which f is not continuous, then the Fourier series still converge, but to converge to the average of the left hand limit and right hand limit of f at x, right? So we have that representing theorem, but we require a condition for f, right? So we require two conditions. The first one is that f is piecewise continuous, okay, in one period, and the f has left hand limit at derivative and right hand derivative at every point. So that even though in practical consideration these two requirements usually is fulfilled. So, for example, it's especially for the electrical signals considered in circuit theory, that if f is such a signal, then the two conditions are always satisfied. But in other discipline, if we want to apply the representing theorem, then we may get into trouble. But for example, for some function f of which is not piecewise continuous period term, or it is not it may not have a left-hand derivative or a right-hand derivative at some point. Okay, so in this situation, we cannot apply the representation theorem. But with the success of the representation theorem, we still want to see how good, even we use a partial function, a partial sum function of this series. Okay, even can we approximate the original function f by a partial sum function of this trigonometric series? Can we do that? And how good it, right? So here we consider no matter whether, right? So we don't need to answer the convergence question or the representation questions. Okay. Right. So no matter it can be conceived to approximate f by a partial sum function x capital N of x, which is equal to a0 plus summation n from 1 to capital N, an cosine nx plus bn sine nx. Okay? So this is our temptation. This is we're willing to do so. But well, you can do you want, but the question is how good it is. All right. So this is the central question. Okay. Okay, so to answer, okay, so any questions about our goal at this moment? No question, all right? Good. So to answer this question, we let Tn, okay, right. So this one is an arbitrary trigonometric polynomial, right? So be an arbitrary trigonometric polynomial of degree you may argue why we call such a function as a trigonometric polynomial. Because polynomial is something that you have power terms, right? So for example, in here, the polynomial for polynomial may be 3a0 plus a1x plus a2x squared plus a capital N x n squared. So we call this is a polynomial of degree n, okay? Of degree n if okay, if the coefficient of the leading term is not 0, so we know this is a polynomial in x. The indeterminants here is x here. And how come? Well, if you see it, it seems like we don't have the so-called power term here, right? But remember, by the multiple angle formula, okay, the cosine nx is equal to a polynomial of cosine, okay, or sine, right? But here we know it's a polynomial of cosine of degree, right? Okay, so we have so for example 2x is equal to 2 cosine square x minus 1, and sine 2x, okay, x2 sine x and cosine x. So here and etc. Okay, I can't remember too many identities. Okay, so we see that this is a polynomial of degree 2 here, and here this is also a polynomial of degree 2. But you should regard sine x and cosine x as two indeterminate. So you can say this is x, this is called capital X, this is called capital Y, something like that, right? And so this is 2. Okay, so it's a polynomial in cosine x and sine x, right? Cosine x. So you will see that cosine nx or sine nx can be represented in this way. Okay, can be represented. Okay. Right. So that's why we call Tn as a trigonometric polynomial. Okay, and the coefficient is capital A0, capital An, capital Bn, can be any value, any complex numbers, so that we call that is an arbitrary trigonometric polynomial of degree n. Okay, so we want to relate. This is just a candidate. Okay. And now we choose a meaningful measure of either of P sub n from F over minus pi pi to pi as follows. Okay, so the measure is that okay, so we have the difference, right? And we take the square of the difference and integral over the defining interval. Okay, and which is okay. All right, and which is called the square adder of T sub n relative to the function f on minus pi to pi. Right. So for an arbitrary trigonometric polynomial of degree capital N, right, and then we use this to measure the adder, okay, of this approximating function to the original function f. Right. So this is give us that. Okay, right. So this is called the square adder, and the goal is to find an optimal trigonometric polynomial of degree n such that the square adder E sub n is minimized. Okay? Alright, so we establish an optimization problem. Okay? Okay. And as you can see, we have two capital N plus 1 degree of freedoms, right? Because there are two capital N plus 1 coefficients, okay, to be chosen. Okay, so that this square adder is minimized. Okay, now we expand the square adder. So now since En, right? Okay, okay. As we know, the compass conjugate this thing can be expressed in here. Okay. Now, so that we have four terms. So this is the integral of the square of f's value of f minus f of x, Tn of x bar dx minus f of x bar and Tn x dx plus Tn of x square. Right, so we have four terms. And this term, the first term is independent of the target trigonometric polynomial, but the rest three terms involve a T7. Okay, so we have to compute this three integral. The first of all, when we compute the integral of the square of the absolute value of the trigonometric polynomial here, okay, so we can do the substitution, right? This one, and okay, and dx. Right, and so that how many terms do we have? Here we have 2n plus 1 terms, and this and here we have 2n plus 1 terms, so that we have a square of 2n plus 1 terms. It's a big number of terms, you can see. But if, the final thing is that we have square plus okay, so that so by the orthogonality of the trigonometric system, in theorem 11.1.1. Okay, so in theorem 11.1.1 we have stated three statements, okay, about the orthogonality of the trigonometric system. Okay, so you finally have this term. And similarly, okay, right, so the computation can be done, okay, with patience, because there are so many terms, right? But I believe you are able to do so. Okay, and similarly, we have that 2a0 bar, little a0, plus summation, and 1, capital N, an bar, little an, plus big N bar, little n. And the last one, okay, you got pi a0 in the bar plus summation and the 1 capital N, an little n bar plus big Bn, little bn bar. Alright, so that just pi. Right, so we have that. And so we have doing the substitution back to this expression, we have plus minus here, so we have okay, we will do something that and you can see this term may well appear in here in these three identities. So this is the technique. We subtract something but add back the same thing for our little purpose. Right, so we do the subtraction and addition here. And the 2, so we do minus pi a bar a0 plus summation n equal to 1, capital N, an bar an plus b bar bn. Okay. So this term minus this term, pi to a0, it's little a0 bar plus summation a n bar little a n. Yep. Plus bn bar. Okay. And plus this one, plus this pi to a0 bar plus the summation n equal to 1, capital N, square plus. Okay. Now we will use these four terms, put them together. Okay. And look at here. This term plus this term minus this term, minus this term, and plus this term can be perfect squaring that. So this becomes 2. So let's see. Y minus pi from here a z square plus summation n equal to 1 and capital N. Okay, and an square. Okay, plus pi. Okay, and 2 a0 minus capital A0 square plus summation n equal to 1 capital N and minus capital A square plus bn minus capital Bn square. Okay. And remember the small a0. What is small a0? Small a0 is here. is the coefficients of the trigonometric field series generated by F. Okay, so this is A0, AN, and the BN. Okay, so this has been given here, right? This one is a constant, okay, and also this is a constant because A0 is obtained from f of x from this integral. Right, so this is given, and deta n is also given, deta bn also given, right? So that the first two terms here are given. Only considers here because A0 is given, deta A0, deta n, deta bn, they are all given, but the variable for optimization is capital A0, capital N, and capital Bn, which is associated Tn. Okay, which is associated Tn here. So our optimization, okay, so this is En here. Okay. Right. So this En, which is a quadratic function of parameters A0, AN, BN. Okay, so it's a quadratic function. And right, and it implies that so you can see for this term always negative, right? So you see that this term is going to 0. Is that right? Why? Because it's the square of the absolute value of this difference. And here this is square of the absolute value of the difference, square of the absolute value of the difference here. Okay, so this is going to be 0. So the minimum, so En as we know, the square error has a lower bound. Which is the difference between this integral and this is sum. Okay, so this is become to the low bound. The low bound here. Okay. And where the equality holds. Right, so the En can achieve the minimum. Right, if only this term is equal to 0. But this term equal to 0 means that the big A0 is equal to A0, big N is equal to N, and big Bn is equal to Bn, for all n equal to 1 to up to capital N. Okay? Right, so this means that if and only if Tn of x is equal to the partial sum function. Okay, for all okay, and so that minimum 10, so that right here, all right, you see that this is actually equal to the square error, right? The square error of the function f from the partial sum function. Right, and we define this is to be En of tilde. Okay, so En tilde is the minimum square error. Okay, so this is the minimum square error. So the minimum over x, right? And which, as we already computed, which is just equal to okay? So this is the minimum square error we have. Any questions up here? So we start with our study from the temptation that we want to use a trigonometric polynomial of degree n to approximate a square integrable function over a finite cosine interval from -pi to pi. So this is our goal. Okay, we want to find them. And to measure the goodness of such an approximation, we use a square error measurement. Okay, so the square error measurement is here. Okay, so here. Okay, and we try to find a trigonometric polynomial of degree n which minimize the square error, right? So this is our computation. So we compute the square error and express the square error, okay, as you can see, that is a quadratic function of the parameters, or the coefficients of the general trigonometric polynomial, right? So that is one. Okay. Unfortunately, because we have this expression, so we can obtain the minimum, okay, of the square error, if and only if that this term is equal to 0, right? Because the first two terms here, they are fixed. Okay. Yeah, fixed. The only variables here, the capital A0, capital N, and capital BN. Okay. And so we find that the minimum value is achieved if and only if that the target trigonometric polynomial is exactly equal to the partial sum function of the trigonometric Fourier series generated by f. Okay, so this tells us that the partial sum function x sub capital N of x plays an important role. Okay, plays an important role because it is the best trigonometric polynomial to approximate our square integrable function f under the measurement of square error. Okay, so we have the measurement of the error. Okay, and in the same time, we are able to find the minimum square error achieved by the partial sum function, which is just equal to this formula here. Okay, so any questions? If not, then we take a break up to 2:20. Okay. So we will summarize the previous discussion in Theorem 11.4.1. Alright, so the score either is sub n of trigonometric polynomial t sub n of degree capital N relative to a square integrable complex real valued function f minus pi to pi is minimized if and only if Tn is equal to Xn. And the minimum score either x en tilde minus pi square plus square plus, okay, so this one. So that is the theorem 11.4.1. Okay, now since the minimum square error always greater than 0, okay, right? So this difference is greater than 0. So we have the following inequality: pi okay. So is this equal to this integral? Okay. Theta A0, theta AN, theta BN, they are coefficients of the trigonometric Fourier series generated by F. Okay. Right, and this is for all capital N greater than 0, greater than 1. Right, so as n goes to infinity, right, as n goes to infinity, then the serial sum will converge. Okay, so the partial sum becomes to the serial sum. Okay, so that this is series, and it's less than equal to the same upper bound. So we have that. Okay, and this is called basis inequality. solve Bessel's inequality. Any questions? Right, so as an application, okay, of Bessel's inequality, right? So we will prove a theorem of uniform convergence and absolute convergence of trigonometric Fourier series generated by a class of square integrable functions. Okay. Okay. Now, in section 1. Especially stated in Theorem 11.1.2, we deal with a special class of absolutely integrable functions, which are functions, first, piecewise continuous, right, in one period of time, and second, that the function has a left-hand derivative and a right-hand derivative at every point in the unequals interval, right? Right. So we deal with a class of absolutely integrable function. Now we will deal with a class of square integrable function. Okay, such that the trigonometric Fourier series will converge uniformly and absolutely. Okay, so the convergence property becomes to be more well behaved. Uniform convergence of a sequence of function has been defined, right? Last Saturday when I delivered a lecture on section number 3. Okay, so I believe you already watched the video recording and learn the concept. Okay. All right. Now, before we characterized such a class of square integrable functions, we have to point out a couple of things. Now, a piecewise, a continuous function f on a finite cost interval AB x square integrable over b. In section number 1, we point out that a piecewise continuous function of a finite cross interval is absolutely integrable over that interval, right? But here we can see that furthermore it is square integrable. Okay, so it's square integrable over AB. Of course, if we prove that a piecewise continuous function is square integrable over AB, then from our previous discussion, this function is also absolutely integrable over AB. Right. Now, so to show this, we let a equal to x0, x equal to b, finite number of points, okay, such that f is continuous on xi minus 1 to xi from 1 to n. Okay. Yep. This is from our definition of piecewise continuous function. Alright, so that f is continuous on each piece. Okay. This is finite open interval. Okay, xi. And the left hand and the right hand limit. Okay, so f of x0 plus. So at x0 we have only right hand limit. But for I equal to 1 to n minus 1, we have both different limit and right hand limit. But at b, at xn, we have only different limits. Okay. Okay. Now define n functions gi xi minus 1 xi by here for gi f of x when I is in the I space, okay, without the excluding the two endpoints, and f of x I minus 1 plus f of x equal to x I minus 1, and f I minus f of x equal to xi. Okay. Alright, so that thus gi of x is continuous on the finite cross interval. Okay, so gi is continuous. And by the extreme value theorem, that gi of x is this equal to m sub I for all x in the finite closed interval. Okay, for some mi greater than 0, greater than or equal to 0. Okay, so now we have now this integral can be partitioned to n integrals. Okay, by partition, and by definition of GI, that in this interval, we have gi of x. Okay, so f of x can be replaced by g sub I of x. And because of the bound here, so that okay. And apparently, this is finite. Okay. Okay. Alright, so now we define a piecewise continuous complex real valued function f on a finite closed interval AB is said to have a piecewise continuous derivative on AB if there exists a finite number of points right, so A is defined to be A0 and A1 and xn is equal to B such that f is continuously differentiable. Okay, on the finite closed interval, finite open interval, I'm sorry, open interval from x sub I minus 1 to x sub I for each I from 1 to n, and the derivative, okay, the derivative f prime xi minus 1, and then xi has a left hand, limit f prime of xi at si, and right hand limit f prime xi minus 1 plus at xi minus 1. So this class of functions have a piecewise continuous derivative. Okay. So let's take an example. Suppose that the finite closed interval a to b can be divided into 3 parts here. Divided into 3 parts. Okay. So, so f of x, as you can see, it's a piecewise continuous function. Okay, so first of all, it's a piecewise continuous function. So f of x will not be a continuous function, but it should be a piecewise continuous function. First of all, and then we can find. So the derivative exists. Right, so consider the 3 open intervals. Okay, so we just consider the 3 open intervals here. Okay, and we have 4 points. X0, X1, X2, and X3 here. And f is continuous differentiable on each open interval, so that in each interval we know this one, so it's a constant. A constant here. Alright, and it's a negative value. Alright, and for this one, okay, so this is f prime of x. And we will see that the function does not have derivative at x0, x1, x3, x2, and okay, another one. Okay, and we have that one. This is 0. Right, so f of x is continuous differentiable in either each of the three finite open interval. Okay, and no problem with that. So they are continuous. And for the derivative has left-hand limit, and the right-hand limits here, and left-hand limit. Right-hand limit and left-hand limit, and also the derivative has right-hand limit at x1, and at s2 it has left-hand limit. Also, for the derivative in the third of interval, it has right-hand limit at the endpoint x2 and left-hand limit at the endpoint x3. Okay, so you see that. So they have a limit. And you can see f prime f of x. Okay. F is not differentiable. At x equal to x0, x1, x2, and x3. Okay. Right. So that so now here, so this example that work, so that has piecewise continuous derivative. Maybe. Okay. Another example. Okay. So f of x is piecewise continuous. Why? Because this is continuous, okay, on the finite open interval a to b, all right, and it's defined x equal a is defined to be 0. Okay, so this is piecewise, but by the way, I'm sorry, it's not piecewise because that it has not that limit So let's see. Okay, it's hard to. Oh, yeah. This one not even piecewise continuous. So, because for piecewise continuous function, in each piece we should have left-hand limits and right-hand limits. Okay, so that so currently anyway, we just consider functions like, but this is just simple example, but we want to consider a function which has a piecewise continuous derivative. Okay, but to have a piecewise continuous derivative, this function must be piecewise continuous. So this is the prerequisite. Okay, this is the prerequisite here. Okay. And as a piecewise continuous function in the finite cost interval, we just prove that this function is a square integrable. Okay, it's a square integrable. Okay, but a square integrable function may not have a piecewise continuous derivative. Okay, may not. So this is a class of square integrable function. Okay. Right. Right. Now, so as this example exhibits that f is not differentiable at this point, so which means that f prime is not defined at x equal to x0, x1, x2, x3, right? Okay? So we can't define a prime. We can't define a prime. But a prime is defined on each of the open intervals there. Okay. So how do we explain? So how do we evaluate how do we define the definite integral? Okay, so how do we define the definite integral here? Because in this integral, we that for such a definite integral, we basically assume that the function f prime of x defined for all x from A to B. Okay? You may exclude A and B, but this function should define at every x intermediate between A and B. Okay? But in here, we know that the function, the derivative does not define at x1, no x2, right? So that would be a problem. Okay, so here we define this integral piecewisely. So that to be the summation okay, because that f prime of x is defined in each piece, okay, and so and this definition is good because that we can show that this is finite. So I would say which is finite things by defining GI X and okay. Okay, so by defining this one, so that which is continuous xi minus 1 to xi, okay, is continuous, and one more. Okay. And this is finite by the extreme value theorem. Because this GI function is continuous on a finite cost interval, so its f value has an upper bound. Okay, right. So each piece, right, is equal to this one and is finite. Okay, since each is finite, so the finite sum is also finite. Okay. So this definition is good. It is well defined. Okay. Any questions? Right, and similarly, right, we defined f prime of x dx, okay, which is okay, and AB f prime of x dx summation. Okay, and AB f prime of x cosine ax dx defined to be summation. So we can still do integrations over the whole finite cost interval, even though the derivative itself is not defined. It is some intermediate point. Okay. Okay. So basically, in each piece, we replace f by g function. We replace the derivative f prime by g function here, like this one. Okay, so this gi function is continuous. Any questions? Okay, so a word can be say that thus if a piecewise continuous function f on AB has a piecewise continuous derivative on AB, then both f and its derivative, okay, square integrable over AB. Okay. Okay. So now we can state the following theorem. This is called uniform and absolute convergence of trigonometric Fourier series. Alright, so let f be a periodic function with a period 2 pi and piecewise continuous minus pi to pi. Okay. Assume that f has a piecewise continuous derivative minus pi to pi, right? Then the trigonometric Fourier series is 0 plus summation from to infinity an cosine x plus bn sin x generated by f. Alright, converges to f uniformly and absolutely on every closed interval, right, on which f is continuous. Now, first of all, f is a periodic function with period 2 pi, and it is piecewise continuous. So it satisfies the first condition required in Theorem 11.1.2. And the second assumption, f has a piecewise continuous derivative, which implies that, so this one implies that f has a left hand and a right hand derivative at each x in minus pi to pi. Okay? Right, so the two conditions are satisfied. Okay, the two conditions required in the representation theorem are satisfied, and so that this trigonometric Fourier series will converge to the average of the right-hand limiter and left-hand limiter of f at each point. Specifically, this Fourier series will converge to f of x, where f is continuous. Okay, so we have pointwise convergence. All right. But if when we have this stronger condition, which means that in each piece f is continuous differentiable. Okay, continuous differentiable in each piece. So this is much stronger, and that then this Fourier series will converge to f uniformly and absolutely on every closed interval. All right, so that it illustrates here. Okay, see here. Alright, so you can see this function is piecewise continuous and has a piecewise continuous derivative. Okay, the continuous derivative. So by theorem EE202001, the series sum is equal to f of x f is continuous. Where f is continuous, and we know it's where f is discontinuous. Alright, so that's is for theorem 11.1.2. But for here, this so for this interval, so we select the interval, say, okay, this interval, So this is AB. Okay, so you can see F is continuous. Okay, on AB. F is continuous on AB. Okay, because in here, this is continuous. So by and so the theorem 11.4.a says that the series converge. So that means that xn of x converge to f, right? Uniformly on AB, and also xn of x converge to f absolutely. Okay? And the uniform convergence, which says that i.e. for all epsilon greater than 0, there exists an m, okay, such that f minus xn x less than epsilon for all x in AB and for all n greater than or equal to capital N. So that the partial sum function will approach to f, okay, uniformly. Okay, means that if we set an error, then this error will be good for all x in this course interval when capital N is big enough. It's big enough. Okay, so this is the meaning of that, and okay. And this means that that xn okay, thumbs up. Okay, anyway, so the proof lecture notes. Okay. And this proof take only 3 pages, so it's a long proof. Okay. But anyway, so the result. So that I think the most important thing is the convergence uniformly. Okay. That they will converge. So the convergence behavior is very good. It's very good. Okay. And the only requirement is that f has a piecewise continuous derivative. Okay. And this is not a big deal. I mean, many practical situations can meet this requirement. Okay. All right. So I'll stop here, and I will record the lectures for for the coming Thursday, because that will be a holiday for you. It's harder for me, but but you are the beneficial from me. Anyway, so you will have the Mid-Autumn Festival starting from Thursday, right? Thursday, Friday, Saturday, and Sunday, so it's a long festival. Good for you. But don't forget to watch my recording, okay? And prepare for the quiz next Monday. All right, so I'll see you in the air. I will see you next Tuesday.